So I keep forgetting that I can orient this iPad like landscape and make a more zoomed in, like a better quality video. So sorry about that for the last few. So if you kind of were getting used to electrophilic addition mechanisms and forming Markovnikov products, and I'm sorry to throw in a curveball here, but we're going to be discussing the hydroboration followed by oxidation reaction today, which is gonna, like I said, is gonna be a little bit of a curveball, and that's Markovnikov. Okay, hopefully you get it. So the regiochemistry is going to be the opposite of Markovnikov, hence it's called Anti-Markovnikov. It is still a specific reaction. It's really just simply an addition of water reaction. In that case, in that sense, it's really similar to oxymercuration, demercuration reaction we just went over, as well as the hydration reaction, right? The only difference, though, is that the regiochemistry is totally the opposite. So this time, let's start with the product and then see if we could explain the regiochemistry. So here's the product we're expecting. And of course, this is also racemic. You get the enantiomer as well, but you get the syn addition of water. So water gets broken up into hydrogen, hydroxy in a way, and then they get added from the same side. That's this reaction. But notice the orientation of the nucleophilic oxygen. It's on the less substituted carbonate added to this, not to that. So that's anti-Markovnikov, and see if we could explain. We're going to see if we can explain that through the consideration of the mechanism. The first thing that you add, just like the name suggests, is a hydroboration or a borohydride kind of a compound. In this case, we're using borane, which is a neutral species that has this structure. I want you to notice that borane, BH3, right? If you draw the Lewis structure, hopefully it makes sense to you that the boron should be sp2 hybridized. Okay. Which means it's trigonal planar in geometry. It's a flat molecule like this completely. And because it's sp2, there is a p orbital that we are not using, or rather borane is not using. There's an empty p orbital here. Okay. So in that sense, this is just like a carbocation. Remember, carbocations have an empty p orbital, right? Meaning this is very electrophilic. Okay. So this is the electrophile that we're using. Remember, this is all electrophilic addition reactions, and what we're going to see is that the pi electrons are going to go for that empty p orbital, which is like a carbocation, but that's going to leave a carbocation and boron fields bad. In that sense, it's very similar to these mercuration reaction. Mercury grabs electrons, feel bad, donates electrons in the form of another bond. Same thing with halogen, grabs electrons but feels bad. It's a nice thief, so like donates a bond back. And similarly, borane is going to donate something back. Now this time there's no lone pair electrons to donate or use, so what it's going to donate is a hydride, like so, kind of like sodium borohydride reaction. Okay. Excuse me. So just to show you the transition state, which sort of determines all the stereochemistry here. Okay. Here's the double bond that's being broken up, and then we're forming a bond between this boron atom and the one of the hydride or hydrogen is going to be added to that carbon simultaneously. Now, part of the reason for regiochemistry here is because boron is grabbing those pi electrons to form this bond. One of these carbons is going to feel like it's going to develop a carbocation like characteristic, right? Between the two, it's going to be this carbon that can bear more of the partial positive charge even in the transition state. Okay, and for that matter, in the transition state, there is a partial negative charge in boron that is partially developing 4 electrons in a way. The other factor in play here, that dagger sign means it's at transition state, is that even sterically speaking, this is a bigger group, BH2, than hydrogen. So the bigger group ends up on less hindered carbon, smaller group ends up on more hindered carbon. That's part of the the regioselectivity here. But maybe we'll say that this carbon gets BH2 less sterically hindered. And this is the carbon that it has more of a partial positive charge, and so therefore it gets the hydride, formerly a hydride. Okay, so that leads to, of course, the regiochemistry. Okay. And another thing I might point out is that this is a concerted mechanism. Why is that important? Well, that means H and BH2 get added from the same side. Simultaneously. So in that sense, this is very much, this part of the mechanism is very much like the very first reaction we discussed in this chapter, the syn addition of 2 hydrogen atoms. They get added from the same face at the same time. It's a concerted mechanism, right? So they get added syn, or the same side. Okay. So that explains not the regiochemistry, but the stereoselectivity or specificity. Okay, so what do you get from that? Well, from that transition state, you get hydrogen and BH2 added on the same side, of course, plus enantiomer. And so this is an Anti-Markovnikov addition. And it's also syn addition. Okay. Now, that's really the product of the first step here. Okay, first reaction. Now, at this point, you're going to add hydrogen peroxide, and the sodium hydroxide, and between the two, what you get from that is peroxide anion that has lost one of the protons due to sodium hydroxide, which is a pretty good base, and this is somewhat nucleophilic. And remember, BH3, boron with 3 groups attached to it, has an empty p orbital like carbocation. It's electrophilic, so nucleophile could coordinate to that. So what do you get from this? Well, you get, maybe I'll draw it over here. That of course puts a negative charge on the boron, right? Now, one of the things I want you to know about oxygen-oxygen single bond is it's notoriously a weak bond. Okay, so maybe we'll add that here. It's not a very stable bond. Oops. So it's prone to breaking, and that's why hydrogen peroxide is kind of reactive, and that's why like it whitens your teeth by reacting with some compounds that are colored or similar things it does to the clothes and stuff like that. But anyway, for this bond to break, right? I hope you can imagine hydroxide might want to act as a leaving group here. It's not a great leaving group, but it could. Now, if that were to happen, this oxygen is going to have only 6 electrons left, and it'll be severely electron deficient, even though it's electronegative, and that's not going to be great, right? It's developing a partial positive charge there. So one of the things that could happen when you have a very electron deficient thing involved is rearrangement. It's kind of like carbocations are prone to rearrangement. For the similar reasons, peroxide is prone to rearrangement. And the way it might do the rearrangement is move this carbon-boron bond electrons over to shift. That does two things simultaneously. Allows hydroxide to leave. This oxygen doesn't have to develop a positive charge, and yet boron gets to get rid of its negative charge all at the same time. So this is a 1,2 alkyl shift. Right, and then you get you will get that. Now, remember the hydroxide just left, and also we have sodium hydroxide in the mixture, so this could attack the now electrophilic boron, because at this point it's got an empty p orbital, right? And once that happens, boron gets to have a negative charge again, and now to get rid of the negative charge, one of the things it could do is just to let go of one of the oxygens, like so. And then what you get is an alkoxide. That, of course, could be protonated by grabbing a proton from the solvent. Okay. So that's the product. Now, what happens to the boron species? Well, this can further react with water, okay, and loses those hydrides, and in the end it just becomes boric acid, which is the stuff that's in borax, essentially. Okay, so that's the mechanism. It's a bit longer one, but once you understand like why it happens, I think it's not too bad. I would encourage you to take some time to figure out the product of this reaction. Now you might ask, well, what the heck is 9-BBN? Well, I'll show you that, and then once you see the structure, I think it makes sense why it's asked in this context. It looks like this. It stands for bicyclo 331 9-borononine. Hence BBN. But it's really just another version of borane, right? The important part is this BH2. Okay, so it works exactly like borane, which is BH3. Notice we didn't have to use the other two hydrogens. Likewise, we don't really have to think about these two carbons attached to boron. It's just kind of there to as a support system, scaffold. Okay, we'll compare answers in the class.